So the last part of the solutions is electrolytes. Electrolytes are free dissolved ions in water. You may remember when we were doing the lab where we got slime and we used slime to determine that it can conduct electricity through a wire that had a light bulb on it. So we had a light bulb and then we had a battery somewhere. It's a 9-volt battery, and then we put that in the water. And when we just had water without salt in it, that light bulb was very weak. However, when we put either salt or if we put Gatorade into the water, then that light was much brighter because it had those electrolytes in the water. So electrolytes are charged ions that are in water. They're biologically important. So potassium, sodium, chloride, um, bicarbonate, calcium, and phosphate are all the ones you should know if you're going to get into medical stuff. And these include polyatomic ions. So these elements, these polyatomic ions, which we learned a while ago, are important again to know. This is the only tricky one because it's a non-metal, but it's positively charged. So that's the one on the assignment that I asked you about. So those, anything that has a charge when it's dissociated in water is considered an electrolyte. If you forget where to get the charge of the um, ions, they come from where they are on the periodic table. And remember, there's a Roman numeral to help you with the ones that are not colored in, right? So the metals that aren't colored in, and then the big split is here between metals and nonmetals. So nonmetals are up in this corner and metals are on the other side. All right. So if a metal, you don't know what the charge is, there should be a Roman numeral associated with it to help you with that. Or it'll give you the formula so you can work it backwards from what the anion is. Okay, so non-electrolytes, therefore, are covalent compounds. So things that come from this area of non-metal, non-metal. And remember, hydrogen actually is a non-metal. Um, so anything with carbon hydrogen is not going to dissociate in water, and therefore it's not going to have charged species and therefore not be an electrolyte. Okay, the last thing we talked about how there's a saturation point for every solid. There's a point where the solid can't dissolve in water anymore. Well, it seems strange if you really think about it that water would just stop trying to pull apart a solid because it's saturated. Water doesn't just go on a lunch break or whatever. It's not sentient, so it's going to just keep trying. So, this idea that there's an equilibrium that happens at saturation is something we want you to understand. So, even though the change is not happening between the solid and the aqueous ions, there is still things happening in the water. Water is still trying to pull apart that solid, and water is also bringing together the dissociated ions at the same rate. So it's sort of like being on a treadmill where even though you're moving, you're not actually changing your position, right? So there's movement of the person on the treadmill, but they're neither moving forward nor back. So there's a thing that will occur at saturation where water will break apart the solid into its dissociated ions, and then it'll bring together those dissociated ions back to the solid. So let's take a look here. There's a little video I posted of this, which I hope to improve upon over the summer, where you can see it has some water um, that will bring ions to the solid. So this is a big solid chunk of NaCl in the water. And as you can see, these ions will be brought in, and at the same time, water without ions will take some away. So here are water molecules. This one's going to take away the sodium. This one's bringing in a chloride. This one's bringing in a sodium. This one's taking away a sodium. This one's taking away a chloride. So the size of this thing doesn't really change. It's just being added to and subtracted from because water doesn't know it's supposed to stop doing that. All right. So moving on. So if the concentration is not going to change, then if we multiply the concentration of the dissociated ions, that will be a constant. And we call that the equilibrium constant, or the Ksp in this case, for the solid. And each solid has a different Ksp. And we can figure this thing out using, if you go on, well, they can be given to you, first of all. which is here. And then recall, because these are negative exponents, that means this will have 10 zeros before the 3, 9, and this would have 5 zeros before the 1, 7. And therefore, this is a larger number than, so this is larger than that. And therefore, BaF2, barium fluoride, will dissolve better in water than calcium fluoride because the dissociation constant, which is the product of the ions, is a bigger number. All right, I know it's not impressive because it's a negative exponent, but it's the way it works. I don't know what to tell you. Anyway, moving on. Oh, and you can see that here, right? The solubility is much better. Huh, look at that. Past Mr. Roach hooked us up. Okay, so another thing that you'll meet in AP Chem is this thing called an ice table. And an ice table will bring up the idea that if you have a solid and it's going to dissociate into its ions, that initially you will have some concentration. So this is saying that the concentration that AGBR dissolves at is 5.74 times 10 to the minus 7. So initially you're going to have 5.74 times 10 to the minus 7 of the AGBR and no AG plus and no BR. So that's before you dissolve it in water. Then for the C in ice, we're going to do a change. And the change is going to occur that all of that dissolves in this case because that's how much will dissolve. And because all of that dissolves, we now will get that same concentration of Ag plus and that same concentration of Br minus. So think about it, right? If you have as part of a avocado toast, one avocado and one piece of bread, then when you take them apart, there's still as much bread and avocado as you had avocado toasts. That was right off. I was jazzing. All right. So then the E stands for equilibrium. So then after everything is dissolved and calmed down, you will have at the end, which is another thing you can think of, no more of the solid and just the two dissociated ions floating around. So that is where that comes from. And then if we want to find the KSP, remember that's equal to the concentration of Ag plus times the concentration of Br minus. So we're just going to multiply those two numbers and you'll find that the concentration or the KSP is like 3.3 times 10 to the minus 13. Are you going to need to do this in this class? Not this year, maybe next year. So if it's not 2022, you might have to do this. All right. So what if there's not a 1-to-1 ratio? If there's not a 1-to-1 ratio, we raise the thing that becomes 2 to the power of 2. All right. So there's 2 BRs for every PbBr2. So therefore the concentration of Br minus would be twice as much as that of Pb. Think about it, right? If you have 2 wheels on every bicycle, then there would be 2 wheels for every body, I guess. And then the concentration of the thing that you have 2 of would be twice as high as that as you have 1. All right, again, not something we're going to get into, but there's that. So the last thing we talked about colligative properties, how ice can't form when you throw salt in it because it sort of breaks up the lattice and it makes it harder for water to form that solid lattice that it wants to form. It's sort of like putting Legos together in a sandbox. It also makes it harder to boil because now you have these charged ions holding back the water, blocking the water from trying to get to the gas phase. So it makes it require more energy to get the water to boil. Anyway, so that's based on particles. So the more little particles you have, right, the more of these little disruptive particles, the more you can achieve these means. So something that's covalent, like sugar, will not break up into more than one particle. So it's only going to have the effect of a 1-to-1. But something that dissociates in water, like magnesium chloride, will actually have the effect of having 3 ions So you'll have three particles breaking that up for every one MgCl2. For NaCl, you would have two particles for every one NaCl. For aluminum nitrate, you would have four, because aluminum nitrate will dissociate into a total of four ions, three nitrates and one aluminum. So now you have four particles breaking apart that stuff as ice, and four particles holding back the water as a boiling thing.